Hello and welcome to the second further maths video on proof by induction, and we're going to look at two examples where you're looking at divisibility statements and then some questions on matrices. So we're asked to prove by induction that 3 to the power of 2n plus 11 is divisible by 4. So we follow the same process as before. We've got 4 steps to take. So n equals 1, check that it's true. So 3 to the power of 2 multiplied by 1 plus 11 is equal to 9 plus 11, which is 20. Make it very clear you understand what divisible by 4 means. It's going to be 4 times an integer, so therefore it's divisible by 4. So it's true for n equals 1. True for n equals 1. We're now going to assume that it's true for n equals k. So that means we can assume that 3 to the 2k plus 11 is equal to 4m, or a different letter if you like, and we can assume that in further work because that's what is a way of writing divisible by 4. We now consider n equals k plus 1. So we're looking at 3 to the power of 2 times k plus 1 plus 11. And we want to be able to use this statement here that we're assuming to be true. So we need to simplify this, and we need to think of this as 3 to the 2k multiplied by 3 squared plus 11, because we can think of this as 2k plus 2, and 3 to the 2k plus 2 is 3 to the 2k multiplied by 3 to the 2. So this is equal to 9 times 3 to the 2k plus 11. Now I want to be able to use this statement here. I want to be able to have that somewhere in my calculations. So what I'm going to do is I'm going to take this 9 out as a factor. So I take 9 out as a factor and I've got 3 to the power of 2k here. I want to have plus 11. But that's going to give me 99. And my expression here that I'm trying to say is equal to only has plus 11. So I need to take away 88. So just convince yourself that if I multiply this out, 9 times 3 to the 2k gives me 9 times 3 to the 2k. 9 times 11 is 99. Take away 88 gives me 11. So this expression here is the same as this expression here. What's this equal to? Well, it's 9 multiplied by 4m minus 88. And we can see that 4 goes into 9 times 4m, obviously, minus 22. This number should always come out to be divisible by the thing you're trying to prove it's divisible by. So, therefore, it is divisible by 4 when n equals k plus 1. So we've done our first step, second step, third step, so we must now do the induction step that says the statement. So if the statement is true for n equals k, then it is true for n equals k plus 1. It's true for n equals 1. We checked that at the beginning. Therefore, it's true for all n in the integers, in the positive integers. So then we've proved this by induction. Now, there is a second way of tackling these questions that I am just going to show you now, because this is sometimes referred to in questions and sometimes the question makes you do it this way. So we start off exactly the same way. We check for n equals 1. So you would write 3 to the power of 2 times 1 plus 11 equals 20 is 4 times 5, therefore divisible by 4. We're then going to say let f of n equal 3 to the 2n plus 11. And we do this to make our notation easier. So we're going to, so now our method is very similar. We're going to assume that the statement is true for n equals k. So if it's true for n equals k, f of k equals 4m. So this is just looking very much like what we did before. This is where the next step is different. What we're going to consider is f of k plus 1 minus f of k. And you'll see the reason why we do this in a moment. So that's going to be equal to 3 to the 2k plus 2 when I put in k plus 1 in there, plus 11, minus 3 to the 2k plus 11. And that's equal to, if you work this out, 3 to the 2k plus 2 minus 3 to the 2k, which is 3 to the 2k on 3 squared, which is 9, take away 1. So this is equal to 8 times 3 to the 2k. What we then say is we can see that this is a multiple of 4, so we might want to write, let's write it out here. So f of k plus 1 minus f of k is equal to 4 times 2 times 3 to the 2k. Now we know from our assumptive step that f of k is 4m. So we've got f of k plus 1 minus 4m is 4 times 2 times 3 to the 2k. So basically what we're showing is if we know the difference of two things is a multiple of 4, and one of those things is a multiple of 4, then this one must also be a multiple of 4. So f of k plus 1 is divisible by 4. So we've used this expression and our assumptive step to get to f of k plus 1 is divisible by 4. Then the last step, the inductive step, is the same. We say that so if the statement is true for n equals k, it will be, sorry, you can't see my writing now, then it's true for n equals k plus 1. It's true for n equals 1, therefore true for all n in the positive integers. So this method of considering f of k plus 1 minus f of k is sometimes used. Sometimes they ask you to do that. One of the benefits of it is that it usually makes the 4, which we're trying to get to in this case, come out in more of an obvious way here than it does here. When we're manipulating the algebra here, we have to do a little bit more work to get the 4 out of the 88. But you should be able to do these questions both ways. Right, the last example, we're going to look at using matrices. These are, again, it's the same routine for these questions. So we're going to say, let's first of all check when n equals 1. So we check when n equals 1, and we say, well, what is a to the 1? That's going to be 1, 0, 5, 1. And so that's the left-hand side. And the right-hand side is 1, 0, 5 times 1, 1, which is 1, 0, 5, 1. So left-hand side equals the right-hand side. So it's true for n equals 1. So the next step, assume it's true for n equals k. So that means that a to the k is equal to 1, 0, 5k, 1. We're now going to consider n equals k plus 1. So we're looking at a to the power of k plus 1, and that's a to the power of k multiplied by a. Now we use what we've assumed to be true in the second step. So a to the k is 0, 1, 0, 5k, 1. And then we put in the matrix A, 1, 0, 5, 1. And this is equal to, so we do the multiplication, 1, 0, 5k plus 5 here, and 1. It's important you make it clear that this here is the thing we're trying to prove with n equal to n plus 1 in there, or k plus 1 in there. So I would rewrite that as being 1, 0, 5 times k plus 1, 1. So we've shown that if it's true for n equals k, then it will also be true for n equals k plus 1. So now we've got the last inductive step. So the statement, so if the statement is true for n equals k, then it is true for n equals k plus 1. It is true for n equals 1, so it's true for all n in the natural numbers. So that's a matrix proof. These ones fairly straightforward. Just be careful with your multiplication here and make sure you show that it's the k plus 1 in place of n there.